right, we're looking at lesson 4 now. The difference between lesson 3 and lesson 4 is in lesson 4, I'm not going to tell you which law to use. That's going to be your responsibility to be able to pick out which one of the 6 gas laws you need to use given the problem that you have in front of you. So first here, I just gave you a space that you can rewrite the laws in here, so you have them all on one page if you'd like to do so, okay? But I'm just going to start right in on the example problems. So the first one says, assume that you have a sample of gas in a container with a movable piston. That means that if you look at this container down here, basically the top can move. It can go up or down, okay? You're going to redraw the container to show what it might look like if the temperature of the gas is increased and the pressure is kept constant. So this one, I'm not asking you to do any math. What I am asking for is the clarification on if you understand how different variables are related. So what you're seeing is that the temperature is increasing, and I want to know what happens to pressure. Okay, so there is a little trick, PTV, if you write it out that way. You can think about if you had like a slip of paper with this on it, okay? And you move one variable, you can see what happens to the other. For example, if I move the paper, like physically pull the paper down so pressure goes down, this end would have to go up, okay? So then volume would go up. Right here, we're looking at if the temperature is increased, so if you push the middle of the paper up, that means that this side of the paper would also move up. Okay, so that's a little trick to help you think about this here. So if temperature goes up, pressure should go up as well. And then in this case, it's asking you if pressure is kept constant, what happens to the volume? So think about, okay, so if temperature goes up and pressure is held constant now, we don't care about that, okay? You push temperature up, volume should also go up. So that means what I'm looking for in this problem is that you show me that the container volume should go up, meaning this lid should move up, okay? So you can redraw something like this, where you show me very clearly that the lid's like all the way at the top. You can show that little arrow here showing it came up, and you can just redraw all the dots in here for gas molecules. You can draw the lines behind them if you want to show that they're moving, okay? But what really matters here is that I see that you show me that the lid went up, okay? The volume goes up. All right, let's get into some ones with some math. So the second example here, sample of oxygen takes up this much space, decimeters cubed, it's just a measurement of space, okay? Which is fine as long as you don't care that your new volume is in that unit. We don't. We'll leave that alone. So we know that's amount of space. That's our first volume. And we have a amount of pressure, which is P1. Okay. Pressure's changed to this, so we have P2. We need to find V2. Okay. So what I did not do here is tell you it's using Boyle's law, but if you label them like I just did, that should be pretty apparent. So I'm going to write out Boyle's law. And I'm solving for V2. Okay, so V2 is equal to P1 V1 over P2. So then I'm plugging things in. So P1 is 500, V1 is 34, P2 is 340. And at that point, you're just calculating. So 500 times 34 divided by 340 means you should have 50. And then your unit's going to match this guy again. So decimeters cubed. Okay, so there's nothing really new. It's just I'm not telling you which law to use. I didn't tell you use Boyle's, but if you label them as you go through the problem, it should be pretty easy. Let's try another one. The temperature of gas changes, its volume decreases from this to this. Okay, so this is the first volume, this is the second volume. If the final temperature, the final meaning it's the second temperature, so T2, remember that has to be in Kelvin, so if we add 18 plus 273, we're looking at 291. What is the initial temperature? Okay, so T1. Now it is asking us to go back to Celsius, but we'll do that at the end. So knowing that we've got volume and temperature, you're going to use Charles's law. But again, I didn't tell you that. You had to figure that out as you go. So V1 T2 is V2 T1. I'm solving for T1 here. So I've got V1 T2 over V2, starting to plug in. So V1 is 12, T2 is 291, V2 is 7. Multiply 12 times 291, divide by 7, you're looking at 499 Kelvin. I did ask you to go back 2 degrees Celsius, so you just subtract 273. So 499 minus 273 is about 226 degrees Celsius. And that would be your final answer. Just one extra step there, but not too bad. All right, and the last example we're going to look at here. So the volume of sample of helium increases from 5 to 25, and the temperature drops from 2000 to 1750. So volume increases from this, so first volume, second volume. Temperature drops, so this is P1, P2. Initial pressure is P1. We need to find the final pressure. So here's a combined gas law problem. So we've got P1, P1, P2, 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 P1. I'm solving for P2. So I have P1 V1 T2 over V2 T1. Okay. Then I just start plugging in. So the first pressure is 1500. My first volume is 5. My second temperature is 1750. Notice these were already in Kelvin, so that's why I didn't have to convert them. The second volume is 25. And our first temperature is 2000. So 1500 times 5 times 1750. Okay. And then I divide that out by 2000 times 25 first. Okay. And then when you do that, you're looking at an answer of about 262.5. And then the units match the other pressure units, so mmHg. Okay, so not too bad. We agree. Hopefully these are making sense to you, and you'll be trying them out on your own when you don't know which law to use.